In section 6.2, we're going to be working with binomial distributions. So we're going to learn how to make a binomial distribution and how to interpret the data that is in a binomial distribution. And our vocabulary is going to be pretty extensive in this section. We want to understand what a random variable is, what is a probability distribution, what is a binomial distribution, what is a binomial experiment, what does it mean when a binomial distribution is symmetric or skewed? Okay, so we're going to talk about all these things as we go forward. So this is, we're talking here now about a probability distribution, and the probability distribution is the probability of any likely thing happening. So in this case, when you take a look at the idea of rolling an individual die, right? A die has 6 sides, and when you roll it, the probability of rolling any one particular number is 1 in 6. They're all just as likely to come up. So we have the probability of a random thing happening. So the rolling of the die becomes the random variable. What am I going to get? It's going to be totally random in terms of which side comes up. And then what's the probability of each of those things happening? So in the case of rolling a single die, then the possibilities are 1 in 6 for each different thing happening. Okay, so this is the probability distribution for rolling one die. We're going to take a look at the probability distribution for rolling 2. So if you look at the possible things that could come up, I can get the number, I could get a 2, a 3, a 4, a 5, a 6, a 7, an 8, a 9, a 10, an 11, or a 12. Okay, so these are the possible outcomes. And if we start thinking about how do those things happen, I'm just going to take a couple seconds here and make a quick table. Right, so what's the probability? How many different ways, let's say, first off, how many different ways is it possible for the dice to come up? Well, there's 6 sides on one and 6 on the other, so the possible outcomes would be 6 times 6, which is 36. So there are 36 different ways that 2 dice can come up. And a 1 and a 1 will give me a 2. That's a chance of 1 in 36. And a 6 and a 6 will give me 12. That also is 1 in 36. Now when you're talking about a 3, the first die could come up 1 and the second one could come up 2. Or the first one could come up 2 and the second one could come up 1. So there are 2 in 36 here. And that's the same over here for 11, right? I can have a 5 and a 6 or a 6 and a 5. That's also 2 out of 36. When we talk about a 4 coming up, we could have a 1 and a 3, a 2 and a 2, or a 3 and a 1. So there are 3 different ways out of 36. And that's similar with the 10. I could have a 6 and a 4 and a 6, or a 5 and a 5. 3 out of 36. Now when we talk about how 5 could come up, I could have a 1 and a 4 or a 4 and a 1, that's 2. I could have a 2 and a 3 or a 3 and a 2, so that's 4 different ways this could come up. And that's the same with 9. I could have a 3 and a 6 and a 6 and a 3, or a 4 and a 5 and a 5 and a 4, and that would be 9. So there are 4 different ways that could come up. When you look at a 6, I could have a 1 and a 5, or a 5 and a 1, that's 2. I could have a 2 and a 4, or a 4 and a 2, that's 2 more. And I could have a 3 and a 3. So that would be 5 different outcomes. And that'll be the same for the 8. And then when you're talking about a 7, I could have a 1 and a 6, or a 6 and a 1. I could have a 2 and a 5, or a 5 and a 2. I could have 3 and a 4, or 4 and a 3, and that's 6 out of 36. Okay, so if you look at, if we got what we have here, I have 1, 3, 6, 10, 15, and another 15 here, that's 30, and the 6 in the middle, so that's 36. I've got this all correct. So this is my probability distribution for rolling 2 dice. Now, if I want to go ahead and take this and make a histogram, that's what it's asking me to do now, is make a histogram. So I'm going to copy this and I'm going to make a new page. And when I paste this in, if it wants me to make a histogram is like a bar chart with no spaces between the bars. So what I want to do then is I want to go ahead and create this histogram based on measurements. And let's just say, we'll say this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 things coming up, right? And then I can have 1, 2, 3, 4, 5, 6. 6 is the maximum number of ways that this comes up, right? So that's as high as I need to go. So when we look at the probability of getting a 1, sorry, 1 was not possible. Let me get rid of 1. And that means I need to take all these guys and I need to move them down 1, don't I? Okay, so the probability of getting a 2, that was 1 in 36. And then the 3 was 2 in 36. And the 4 was 3 in 36. And the 5 was 4 in 36. 6 was 5 in 36. And then the 7 was 6 in 36. And then my other side, oops, I was going by 2s and then I made a mistake, didn't I? So there's the 6. And the other side is the same, right? It matches. So this gets back into the concept of when we put together a distribution, when it's shaped like this, where it's even on one side or the other, this is what's called symmetrical. Okay, so my handwriting isn't so great. I didn't draw really super straight lines, but this now is a histogram that shows the probability. And it's very clear that the most likely thing for you to roll is a 7. That's the most likely thing that you're going to roll when you roll 2 dice. Okay, and you can see that it sort of falls off on either side. So the least likely thing is to roll a 2 or 12. The most likely thing is to roll a 7. Okay, so when we want to interpret it, we just talked about this. What's the most likely sum when rolling 2 dice? It's a 7. What is the probability that the sum of the 2 dice is at least 10? So at least 10, that would be 10 or more. So if you take the probability of 10, 11, and 12, these guys, I would have 3, 5, 6 in 36. So that would be 6 in 36, or 1 in 6 would be the correct way to put that when I simplify my fraction. Okay, so we created a binomial distribution. Oops, excuse me. We created a binomial distribution for the probability of the result of rolling dice. And then we interpreted this information by looking at the graph we've made and the table we've made and using it to answer questions. Okay, so I want you to practice doing that. Do problem 3 and then problems 6 through 9. Those all deal with one binomial distribution. So go ahead and practice this a little bit and then come back. Now when we start talking about a binomial distribution, a type of binomial distribution, a type of a probability distribution is a binomial distribution. And a binomial experience meets the following conditions. There are a certain number of independent trials, meaning by independent, that's an important term. Trials are independent when each time I do the new trial, the probability doesn't change from the time before, meaning the new probability is not dependent on what had happened before. So for example, when I roll dice, each time I roll the dice are exactly the same. So if I roll dice 10 times, those are independent trials because each time I roll the dice, it's exactly the same. On the other hand, if I deal cards out of a deck, this would be a dependent set of trials because each time I pull a card out of the deck, the probability changes for the next trial because there are less cards in the deck. So the probability of getting any specific card when I deal out of a deck the first time is 1 in 52. But then when I deal a second time, it's going to be 1 in 51, and then 1 in 50, and then 1 in 49. So the probability changes, and the new probability is dependent on what happened before. So those are the difference between independent trials and dependent trials. Now, when we're looking at these independent trials for a binomial experiment, the trial has only two possible outcomes, success or failure, meaning we're measuring something specific, and that there's the probability of success that is the same for each trial. So the probability of something happening is denoted by P for probability. And the probability of something not happening is 1 minus P, which would be 100% minus the other probability. So if the probability of success is 40%, 0.4, then the probability of failure is 0.6. That makes sense. And then for each binomial experiment, we can calculate the probability for each individual thing happening, meaning exactly K, by using the combinations and the probability to the power of K, probability of success to the power of K, and the probability of failure to the power of n minus K. So we're going to use this little formula, and we're going to make a binomial distribution. So let's take a look at what we have. So in this case, 41% of US households have a soccer ball. So that means the probability of somebody having a soccer ball is 0.41. That's 41%. And that means that the probability of them not having a soccer ball is 0.59. Okay, if I conduct 6 experiments, I ask 6 randomly chosen households whether they have a soccer ball. That means that n is equal to 6. And we want to draw a histogram of the binomial distribution for our survey. So what are our possible outcomes? We could have 0 houses, right? We could have 1, 2, 3, 4, 5, or 6 that have soccer balls, right? Those are the different possible outcomes that we could have. I'm going to just get the 6 and the 5 apart from each other there. So if I want to go through now and find out the probability of these things happening, I'm going to want to do this formula here now 7 times. Okay? Or I could go back to Pascal's triangle. If you remember Pascal's triangle, I could use Pascal's triangle to find the combinations. Okay, and that might be even easier. So I'm going to pull up Pascal's triangle. So if I go back and take a look at the book, I have Pascal's triangle here, but the book only gave me Pascal's triangle to the 5th level. If I want the 6th level, I'll have to add. So I'll have 1, 6, 15, 20, 15, 6, and 1. So let me go back and put those down. So my combinations would be 1, 6, 15, 20, 15, 6, and 1. So that's this part right here. So I could calculate the combinations, but I have Pascal's triangle. I didn't have to do that. I went ahead and I looked at Pascal's triangle and just pulled the values. Right, then I'm going to have 0.41, in this case to the 0 power, times, so the probability of success to the 0 power times the probability of failure to the n minus 1 power. So, I'm sorry, n minus k. So in this case, if k was 0, and 6 minus 0 would be 6. Right? And we're going to go through here, and what's going to change is these powers, right? So here will be 1, and this one will be 5. And you'll notice, like when we were working with the binomial expansion, you see how these are always going to add up to 6? 0.41 squared times 0.59 to the 4th, 0.41 cubed times 0.59 cubed, 0.41 to the 4th power, 0.59 squared, 0.41 to the 5th power, 0.59 to the 1st, and 0.41 to the 6th power, 0.59 to the 0 power. Okay, now the 0 powers are easy. This becomes 1, and then I'm just going to have to take this to the 6th power. So let me get a calculator out. And then I can start calculating these values. So I know I'm going to have 0.59 to the 6th power, and that's going to be times 1 times 1. So I'm going to have 0.03. So 0.03, or 3%. Okay, and let's do the next one. I'm going to have 0.59 to the 5th power times 0.41 to the 1st power, which is just 0.41, times 6. And I have 17.6%. And actually, I'm going to put them in here as percentages instead of as decimals. 17.6%. Oops. So now I'm going to do my next one. I have 0.59 to the 4th power times 0.41 squared times 15. Oops, it looks like I made a mistake. So let me do this again. I know I made a mistake because this percentage would increase at this point. So 0.59 to the 4th power times, and let's use parentheses, 0.41 to the 2nd power, close parentheses, equals, times 15 equals 30.55%, or 30.6%. 30.6%. I'm going to do this guy again. So now I'm going to have 0.59 cubed, 0.59 cubed times, open parentheses, 0.41 cubed times 20. And I've got to do it 3 more times. And what I'm going to do is I'm going to go ahead and stop the recording while I go ahead and do the math 3 more times and fill out the table. And then I'll come back to you. Okay, so I finished out my table, and you can see that the probability of there being 4 households with soccer balls is 14.8%. 5 soccer balls is 4.1%. And all 6 houses have a soccer ball is 0.5%, so 0.5%. Now we want to interpret what we've got. Now I didn't draw the histogram yet. I could go ahead and do that, but if I just wanted to go ahead and sketch that, 1, 2, 3, 4, 5, 6, And then the highest percentage I had was about 30. So if I do 10, maybe maybe 5, 10, 15, 20, 25, 30, 35. If I go up to 35%, so the probability of 1, or 0, sorry, 0, was about 3%, and the probability of 1 was 17, and the probability of 2 was 30.6, so just a little over 30, right about there. And the probability of 3 was 28, so a little under 30, about there. Probability of 4 was 14.8, so almost 15, right about there. And the probability of 5 is 4, so just a little under 5. And of 6 was just 0.5%. It was really dinky tiny. Okay, so now when you look at this histogram, you'll see how it's not symmetrical. Let's go back and look at the other one we drew. And you see how this one is nice and symmetrical. It's totally symmetrical. This is the center. The left half is the same as the right half. But when you take a look at the one I just drew, you see that it's all pushed off to the left. So this is called skew, and this distribution is skewed to the left. Right? So that's the difference. If you go back to our vocabulary, we were talking about symmetrical and skewed distributions. This is a skewed distribution, and the other one I did for you was symmetrical. But let's answer our questions. What's the most likely outcome of the survey? Most likely outcome is that 2 houses have a soccer ball. And what's the probability that at most 2, meaning 2 or less, would be 30.6 plus 17.6 plus 3%. So 20.6, 50.6, 51.2% is the probability that the most I will have is 2 households. So that would be everything from 2 and less. Okay, so this is how I create the table, how I put it into a histogram, determining whether it's skewed or whether or not it's symmetrical, and then interpreting the data I've created. So go ahead and practice this. Do problems 19 and 20. Come on back, and we got one more thing to work on. So we want to do 2 different binomial distributions here for 8 trials when the probability is 0.5 and when the of success is 0.5 and when the probability of success is 0.9. So that means that if n is equal to 8, p is equal to 0.5, and p is equal to, 1 minus p is also equal to 0.5, equal likelihood of success and failure. And I want to compare it to n is still 8. The difference here is that the probability of success is 0.9, and that means that 1 minus p, the probability of failure, is 0.1. What will this look like? Now, again, I don't think you need to watch me work the calculator for these 8 different calculations. I'm going to get the combinations out of Pascal's triangle, and I'm going to go ahead and do the calculations for each of these, and I'm going to build my tables. So just remember that the formula I'm using is this formula here. In fact, I'm going to go ahead and I'm going to copy it, and I'm going to bring it over here. Right? So I'm going to use this thing, and I'm going to have to use it 8 times, and I'm going to build a table, and then I'm going to build a histogram for each one, and then I'm going to come back to you guys. So you're not going to watch me do that. I'm going to assume by now you know how to do these things. Okay, so I took the time to finish filling out the tables for both different situations and drawing the histograms. Now, I want to be explicit about the things I did while you weren't watching, because frankly, I'm not going to go into a calculator and do all this work. There are better tools for that. So I went into Excel and I made a table. So I put in my probability of success and my probability of failure in both cases. I went back to Pascal's triangle. I just took some really quick notes. We had found the 6th level of Pascal's triangle for an earlier problem. So I went ahead and created the 7th and 8th level. Remember, 1 plus 6 is 7, 6 plus 15 is 21. So I went and found the 8th level, and I put these coefficients, the combinations from Pascal's triangle. So I didn't calculate the combinations 8 times. That sounds like too much work to me. I went and used Pascal's triangle because I could. And then I made this table with Excel where I took the probability of success to different powers, right, and the probability of failures to different powers, and I multiplied them all out, and this column here gave me my percentages. Then I went back to the table and I filled out the tables based on what I had in Excel, and then I drew the distributions. So you can see this is a symmetrical distribution. So if they want me to describe the shape of the binomial distributions, this one is symmetrical and this one is skewed to the right. Okay, so go ahead and practice that. Do problems 33 and 34. That's the end of 6.2.